Hello, everybody, and I just want to welcome you to yet another notes video. This one is going to concentrate all on mole math. If you enjoyed our lessons on dimensional analysis and factor label method, conversion of units from earlier on in the school year, you will love this stuff. If you did not, don't worry, it is just more practice. So, that is what we're going to be covering today. We're going to be talking about mole math, how to use mole math as a conversion factor, exactly what mole math is, who came up with it, and all of that wonderful and exciting stuff. And you cannot have mole math without having a mole. And I know I missed mole day, but that is what we're going to be talking about today. And what mole math essentially is it is counting by weighing, okay? Counting by weighing. And that gentleman right there, that gentleman is Amadeo Avogadro. So I would suggest that if you guys can, you take a look at those 4 links down below. They are some videos. They are some mole math songs. Bring a little smile to your face. Hopefully you can enjoy those. Hopefully you enjoy those. And yeah, that is about it. So, the mole, let's see, the mole relates the mass of a substance to the number of particles present. It is similar to a dozen. So when we say, hey, you have a dozen eggs, how many eggs do you have? You have 12. A dozen represents a set number of something. A dozen eggs, a dozen paper towel rolls, a dozen tissue boxes, a dozen calculators. It always means 12. 12 calculators, 12 eggs, 12 paper towel rolls, 12 tissue boxes. A dozen is a set number. Well, a mole is also a set number. If you have a mole of calculators, if you have a mole of paper towel rolls, if you have a mole of tissues, a mole of remote controls, a mole of water bottles, you're going to have the same number of all of those because a mole represents a very specific number of things, okay? So we're going to figure out a dozen. Well, we know a dozen is 12, and a mole, we're going to figure out what exactly that is. So a dozen, well, that's 12, and let's say we have 12 eggs. When we talk about a mole, we're talking about molecules and atoms. When we talk about a mole, we say we have 6.02 times 10 to the 23rd. An extremely, I cannot stress this enough, an extremely important number. 6.02 times 10 to the 23rd. So important that I'm going to get a whiteboard. Oh, that was loud, right in my ear. And I'm going to write on that whiteboard, it is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. Okay, 6.02 times 10 to the 23rd. Really, really, really important. Okay, so that is referred to as Avogadro's number. Okay, now I wouldn't go and suggest you calling Mr. Avogadro, Amadeo Avogadro, by dialing in 602-1023. You don't have an area code, number 1. And number 2, Amadeo Avogadro, he lived back in like in Italy in the 1900s, and he's not alive anymore. So you're not going to get to talk to Amadeo Avogadro. I'm sorry, but you really just need to know his number, 6.02 times 10 to the 23rd. Whoa, really important right there. All right, let's keep moving on. Amadeo Avogadro, why is 6.02 times 10 to the 23rd his number? Well, he didn't actually come up with this number. He didn't propose this number. He actually proposed something a little bit different that we're going to talk about at the end of this PowerPoint. It has to do with gases. It's still along the idea of the mole, but this number, 6.02 times 10 to the 23rd, that was actually named in his honor. I'm just going to keep holding this up here until it's like, you need to know this number, 6.02 times 10 to the 23rd. You need to know it. Sorry, you need to know it. 6.02 times 10 to the 23rd. So it was named in his honor by Jean Perrin in 1909, and the guy who actually came up with it was Johann Joseph Loschnitt. Now, I apologize if anybody actually knows how to pronounce those names. I'm sure you could do it in a much better way than I can. I apologize if I have mispronounced them. But Amadeo Avogadro didn't really come up. This is only his number in name. It was named in honor of him. Okay, he didn't come up with it. He came up with something different, equally as important, but not this number. Not this number. Okay. So moving on. If we had Avogadro's number, and what is Avogadro's number? 6.02 times 10 to the 23rd. If we had that many avocados, what would we have? How many would we have? And remember, that exponent right there, times 10 to the 23, that means we're following that decimal 23 times. So it would be 6.602. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. It's that many, guys. It's that many, okay? So when we say 6.02 times 10 to the 23rd, we're talking about this many. It fills your screen. I really hope this is like writing the right way that you guys can actually read this. Because it looks reversed to me right now, but hopefully it'll flip when I, in post editing. But anyway, 6.02 times 10 to the 23rd. Okay, a lot. 6.02 times 10 to the 23rd. So how many avocados would we have? 6.02 times 10 to the 23rd. It's a lot of avocados. You know what you can do with that many avocados? Make a whole lot of guacamole. Am I right? Am I right? Mole? Get it? Mole? No? No? Nothing? Nothing at all? Really? I think it's funny. I think it's funny. All right, anyway, let's keep moving on. So how many avocados would you have in 1 mole? That many. Please remember that no matter what we're talking about, how many water bottles in 1 mole? How many mice, right? Computer mice in 1 mole? How many markers in 1 mole? It's always 6.02 times 10 to the 23rd. Extremely important. It's going around in circles. And it's going to keep this right here. Okay, let's see. It works like a conversion factor. Really, really, really important. So think of it this way, right? We have a dozen eggs. We're back to a dozen. Okay, I need a eraser here. I'm going to erase this side because we need to remember 6.02 times 10 to the 23rd. I'm going to say that number so many times it's going to drive you nuts. Okay, so we have a dozen large eggs. How many eggs is that? You're right. It's 12. So we have a dozen large eggs. Let's put a big L there, right? And that 1 dozen large eggs equals 1 kilogram of mass. So for every 1 dozen large eggs, it weighs 1 kilogram. Sorry about the glare. There you go. Maybe not. Keep it tilted a little bit. Okay. Now, on another note, we have a dozen, which is 12 small eggs. Does that have the same mass? Does a dozen small eggs have the same mass as a dozen large eggs? No, doesn't have the same mass, okay? So put that in the back pocket for 1 second, because we'll get back to larger and smaller, but put that in the back pocket. So let's think about, there we go. Now if I have 2 kilograms, if I have 2 kilograms of large eggs, how many dozen do I have? Remember, 1 dozen, 1 DZ, 1 dozen large eggs is 1 kilogram. So how many dozen if I have 2 kilograms? 2 dozen, which you know to be 24 large eggs. All right. So you see how we just made that relationship? We actually counted how many eggs there were by knowing the mass. This is what I meant in the very first slide by we're counting by mass. Okay, that's what this is all about, counting by mass. Whoa, it's like I wrote this PowerPoint. Crazy. I know. All right, let's keep moving on. So what's Avogadro's number, guys? What is it? What is it? What is it? 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. All right, here we go. 12 grams of carbon is 1 mole of atoms. Okay, now how did I just get that? How did I make that up? I'm gonna get another whiteboard here. How did I get that? Did I just make that number up? Did I just make up the 12.01? No, I got it from a very specific spot. Did I, in fact, I'm gonna get it right now. Did I magically just pull it out of thin air? No, not at all. No, I looked at something very, very important. Okay, I looked at this, the periodic table. Okay, the periodic table is going to help us get, oof, this eraser, got all like eraser marks on my desk. Gonna have to clean that. Anyway, the periodic table is going to help us get all of the molar masses for all of the elements, okay? All of the elements. Take out your periodic table for me. If you find carbon, you will see that carbon's molar mass on your periodic table, right? It'll be like this. Carbon, you'll probably see something like that, right? You'll see carbon, and you'll see 12.01, and it'll say C. Well, that 12.01, as you can see on the PowerPoint, is the amount of grams in 1 mole of carbon, okay? In fact, if I were to ask you what is the mass of any element in 1 mole, you just look to the periodic table and you get the mass, the average atomic mass, right off the periodic table. Okay, my second question, I already kind of put it up there. How many atoms is this? How many atoms, molecules, particles are in 1 mole? Avogadro's number, 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. Very, very important. 6.02 times 10 to the 23rd. So, do this one for me. Find lead on the periodic table, Pb, and I want to know how many grams of lead are in 1 mole. And if you said 207.2 grams of lead are in 1 mole, you're correct, right? You went to the periodic table, you found lead, Pb, right there. You found lead, and you read that 207, I realize it's out of focus, I apologize. You read that 207.2 grams from the periodic table of lead are equal to exactly 1 mole. Now I could ask you, how many atoms is this? And then you would politely say to me, well, Mr. Fabianski, there are 6.02 times 10 to the 23rd atoms in 1 mole of lead. There are 6.02 times 10 to the 23rd atoms in 1 mole of zinc. There are 6.02 times 10 to the 23rd atoms in 1 mole of carbon, in 1 mole of iodine, in 1 mole of iron, 1 mole of magnesium. Okay, that's Avogadro's number. 1 mole of a more massive atom is going to have a greater mass. And I just want you to understand that as we get further down on the periodic table, the masses will be greater, but it's still always equaling 1 mole. Still always equals 1 mole. All right. So molar mass, very, very, very important. Oops, sorry. Molar mass is a very important idea. It's the mass of 1 mole of any element. We get that from the periodic table. It's always stated in grams, and it allows us to convert between mass and the number of moles. All right, so practice with me. get out your handy dandy periodic table. What's the mass of 1 mole of calcium? Look it up. Ca. The mass of 1 mole of calcium is 40.78. Yours may say 40.08. You could just change that on your periodic table. I apologize. Some periodic tables it's 0.78, some are 0.08. What's the mass of 1 mole of sodium? Na, upper left-hand side of the periodic table. Mass of 1 mole of sodium is 22.99. Mine says 22.990. What's the mass of 1 mole of potassium? That symbol would be K, left-hand side. Mass of 1 mole of potassium is 30.098, 30.10, round up. Okay, the atomic mass is always stated in grams. It's always found on the periodic table. And please understand that regardless of if I were to ask you how many atoms are in 1 mole of calcium, how many atoms are in 1 mole of sodium, how many atoms are in 1 mole of potassium, your answer would always be 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. Very important, right there. All right, so before we do this next slide and we do a little math here, we will break to commercial and I will see you guys in just a moment. Oh, hello there. I didn't see you. Well, welcome to the chemistry lab. Have you ever felt that maybe your chem skills are a little down and out? Maybe that you're not quite understanding all that you need to know about chemistry. Are your math skills not up to the level where you think they can be? Well, I have a great product I want to introduce you to. It's called the mole. Yes, in the mole, we can use Avocados' number of 6.02 times 10 to the 23rd to convert between units. Those units would be grams to moles, moles to atoms. It's a wonderful thing, and I'm hoping you will buy it for just the small price of 6.02 times 10 to the 23rd dollars. A price that is not given out to everybody, but is a special offer. Looking at the periodic table, remember, you can find the number of grams in 1 mole of any atom by finding their masses. It's a wonderful resource brought to you by the Chemistry Classroom. I appreciate you joining me today on this infomercial for the mole, and we will now return you to your regularly scheduled show. Hi, everybody, and welcome back. Welcome back. I hope you enjoyed that commercial. Remember, guys, be wary of infomercials and those weird salesmen. You always got to be careful what they're trying to sell you. So anyway, let's get back to this stuff. So for carbon, looking at the periodic table, my resources here, looking at the periodic table, we see that carbon has a mass of 12.01 grams, and that's per 1 mole. We got that right from the periodic table. So going forward, we can calculate the number of moles in 56 grams of carbon. We're going to approach this just like we did when we had dimensional analysis or conversion factor label and converting between units. What do we want? We want moles. So X moles of carbon, what do we have? 56.00 grams of carbon. That's how we're starting off. X moles of carbon equals 56 grams of carbon. Then what we're going to do, I'm just going to write it a little bit smaller. 56 grams of carbon. Now we're going to look. What unit has to go on the bottom in order to cancel? The grams of carbon. And what's going on top? We want to go to the mole of carbon. Now, if only we had a relationship between grams and moles. If only we had a relationship between grams and moles. You're right. 12.01 grams is equal to 1 mole. So we can put that right in there. 12.01, 12 point, there's supposed to be a point right there. Apologize. 12.01 grams of carbon is equal to 1 mole. Notice the grams of carbon cancel, and we're left with just moles. And then if we multiply all of that out, we get 4.663 moles. Remember that we have 4 sig figs to start with, 56.00. So we're going to get 4 sig figs to end with. Let's do the next one together. Calculate the number of grams in 2.4 moles of carbon. This time, what do we want? We want the number of grams. So X grams of carbon equal 2.4 moles of carbon. What has to go on the bottom in order to cancel? Correct, moles of carbon. And we want to go to grams of carbon. And remember, we have our relationship, 12.01 grams for every 1 mole. The moles cancel. We just have to multiply, and we get 29 grams of carbon. All right, excellent job, guys. Excellent job. This is the conversion. So I would like you guys to try these for a quick second on your own. Feel free to pause the video. I will join you back here in just a little bit, and then we can take a look and go over some of these questions. So I'll see you guys in just a little bit. All right, everybody, welcome back. So let's take a look at these questions. So for number 1, what is the mass of 1 mole of each of the following elements? Remember, you're finding the mass of 1 mole. You're looking at the periodic table. So calcium, 1 mole of calcium. Actually, let's actually write that out. 1 mole of Ca. Looking at our periodic table, we see that 1 mole of Ca is 40.78 grams. 1 mole of aluminum, looking at our periodic table, Al, 26.98. 98 grams. 1 mole of chlorine, Cl, is 35.45 grams. And then 1 mole of krypton, Kr, oof, I have to apologize, I'm writing like pointing at it, writing. 1 mole of krypton is 83.80 grams. All right, not too bad. Okay, let's keep on keeping on. So let's try now. Let's go to number 2. Oh, where's delete? Delete, delete. There we go. Okay, number 2. Change it up. Let's get a little, let's go with maybe a, what do you guys think about a light blue, huh? Maybe try that color. I don't know where that one went. Okay, anyway. All right, so number 2, how many moles are, okay, so X moles of nitrogen equal 32 grams of nitrogen. What unit has to go on the bottom? Grams of nitrogen, and we want to go to moles of nitrogen. Looking at our periodic table, because the periodic table is where we get the relationship between grams and moles, we find nitrogen, and it happens to be right there, and we look, and we see that 14.01 grams of nitrogen is 1 mole. We cross out the units that are similar, and we're left with moles of nitrogen, and we wanted moles of nitrogen. And when we go through, oopsies, and when we go through and we divide 32 divided by 14.01, remember we started with 2 sig figs, so we're gonna have 2 sig figs in our answer. 2.3 moles of nitrogen. And that's our answer. Very good, right? Okay, let's move on to number 3. Let's go with this one. 3. How many atoms are there in 6.6 moles of iron? Okay, so let's see. How many atoms? So X atoms, I'm just going to do a big A for atoms. X atoms of iron, Fe, equal 6.6 moles of iron. Regardless, what has to go on the bottom in order to cancel? That would be mole of Fe. Now, the question becomes, what is the relationship between atoms and moles? And if you remember correctly, that relationship is very important. It is Avogadro's number. 6.02 times 10 to the 23rd atoms equal 1 mole. And that is the same regardless of what element you are talking about. If we're talking about iron, 6.02 times 10 to the 23rd atoms of iron are in 1 mole. If we're talking about carbon, 6.02 times 10 to the 23rd atoms of carbon are in 1 mole of carbon. If we're talking about mercury, 6.02 times 10 to the 23rd atoms of mercury are in 1 mole of mercury. That is the conversion factor. That is a given conversion factor. And it could be atoms, it could be particles, it could be molecules. It's all the same. So if we multiply this out, oopsies. All right, there we go. If we multiply this out, remember how to multiply it on your calculator. Cancel that out first. We're going to do 6.6, and then we're going to do times 6.02 second comma to get the little e, right? I will show you my calculator in just a second. That way you guys can make sure you have it entered in the same way. Okay, so there we go. Hopefully that's pretty clear for you. 6.6 times 6.02 e to the 23rd. We get, and 2 sig figs, it's actually 3.9732 times 10 to the 24th. However, we're going to round 4.0 times 10 to the 24th, and those are atoms of iron. Okay, good job. So let's continue to move on. We're going to finish up this last one, and then we're going to do 2 more PowerPoint slides, and that is it for today's notes. All right, number 4, what is the mass? So this is a 2-stepper, guys, 2-stepper. Our first one, X grams of neon equal 2.6 times 10 to the 15th atoms of neon. All right, what I'm actually going to do, I'm going to mess with the screen a little bit. I'm going to take me, move me up here. I'm going to take this screen, I'm going to disappear and move this screen like so, so I can actually kind of write this out a little bit more. This is live, guys. This is happening live as we speak. Whoa. All right. So now we can actually do this out a little more. So, because it's a 2-stepper, very important, atoms of neon on the bottom, and we always go to moles. Moles is our bridge. Moles allows us to go in between. Mole of neon. Put that L a little bit closer to mole. Okay, for every 1 mole of neon, how many atoms do we have? How many molecules do we have? How many particles do we have? If you said Avogadro's number, you are 100% right. 6.02 times 10 to the 23rd atoms of neon. And those atoms cancel. Now we have to cancel mole, and the only way to do that is to put mole of neon on the bottom. And that's going to allow us to go to grams of neon. And where do we find that? The periodic table. Find any, it's right there. And you will see that for every 1 mole of neon, it is 20.18 grams of neon. And that allows us to cancel out the moles. We wanted grams of neon, we got grams of neon. Everything on top is multiplied, everything on the bottom is divided. And when we go through and do this, let's see, 2.6 times 10 to the 15th times 20.18 divided by 6.02 times 10 to the 23rd. And we get an answer of, oopsies. My bad, guys, hold on 1 second. There we go. We get an answer of 3.26 fixed to begin with, 3.2 times 10 to the 40th grams of neon. All right, so hopefully you guys kind of muddled your way through there. Hopefully this has helped by going over them. I'm going to take a quick little break. It's going to go black for a second, and then we're going to come back and we're going to finish up these 2 slides, and we will be done with these notes. So be right back, guys. And we are back with 2 more slides and 1 more note. So one more thing. We've talked about grams. However, our friend Amadeo Avogadro, he proposed this relationship, and it's a mole to gas relationship, okay? In a gas, particles, as you remember, they spread out as far as they can. They try and get as far away as possible. And that ding means those particles are trying to get away as far as possible as they can. So Avogadro proposed that any gas at the same temperature and pressure, those gases will have the same number of particles or molecules or atoms. See where I'm going with this, right? Particles, molecules, atoms. Avogadro's number, 6.02 times 10 to the 23rd. Don't forget, boom, 6.02 times 10 to the 23rd. You thought it was gone? It's never gone. It's always there. 6.02 times 10 to the 23rd. All right, so 6.02 times 10 to the 23rd. 1 mole of any gas would occupy the same volume as 1 mole of any other gas. Okay, so if I said to you, I have a gas of, I have a mole of hydrogen gas, that's going to occupy the same volume as a mole of neon gas, as a mole of krypton gas, as a mole of chlorine gas, argon gas, oxygen gas, nitrogen gas. They will all, 1 mole, occupy the same volume. Doesn't matter what type of gas they are. So how much is that? Well, 1 mole of any gas at standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure. It has a volume of 22.4 liters. 22.4 liters. This is known as the molar volume. So how many moles of helium are in 22.4 liters? 1 mole. How many moles of helium would be in 44.8 liters? 2 moles. This is like we're doing the same thing over again, guys. We just made yet another connection, okay? So, I don't know why. Oh, how many atoms? Sorry, I didn't even read that. How many atoms of helium now are now in 22.4 liters? Okay, think about this. Make the connection. How many moles are in 22.4 moles? 1 mole. 1 mole is 22.4 liters. Now, how many atoms are in 22.4 liters? Well, if 1 mole was in 22.4 liters, and we know that Avogadro's number of atoms is equal to 1 mole, 6.02 times 10 to the 23rd, then we must be able to say that 6.02 times 10 to the 23rd atoms, particles, molecules of helium gas are in 22.4 liters. Okay. Guys, I hope this has helped. 6.02 times 10 to the 23rd. I hope this has helped please take time and go through your questions, your mole math questions. Remember your conversion factors. Remember, you get molar mass, the amount of grams per 1 mole. That comes from the periodic table. The amount of atoms, molecules, particles in 1 mole is Avogadro's number, 6.02 times 10 to the 23rd. And the amount of liters in 1 mole is 22.4 liters. So those are all very important conversion factors. All right, everybody, have a wonderful day, and I will see you on the next installment of As the Chemistry World Turns. See you, everybody. Take care. Bye-bye.